I'm going to work a few problems for you. So I'm going to pause the video and then go to the next page. Now, these problems, I'm on page 6 here. These problems can be pretty challenging. Okay, we have to be kind of careful here. Now, you know, the important thing is to kind of read carefully and then again circle things. But now we've got things that are horizontal and things that are vertical. So we have to be kind of careful. All right, so I'm going to kind of slowly go through these two problems really with you here. The young college student atop the dorm angrily throws her history notebook from the roof of the building in a horizontal motion. She throws it at an amazing 8.25 meters per second. Now, this problem is based on something I kind of saw up at KU. All right, I saw this kid throw this notebook. It really wasn't on top of the dorms, but I thought that would make an interesting problem. But I did see this kid throw the notebook and it went right into the trash can. So now let's think about that 8.25. What exactly is that? She's throwing the notebook at that speed. Look at the units, meters per second. But she's throwing it off in a horizontal motion. So she's up here on the dorms and she's throwing that notebook off. So this really represents a V sub x. Okay, so we've got this trajectory kind of like this. So it says then, let me back out the video a little bit. It says then that the physics student quickly runs over with the trash can to catch the notebook. All right, so we've got then this type 1 trajectory. And we said then if we could draw pictures of that notebook over time, it's going to have a V sub x. And that V sub x is not going to change if we neglect air resistance. So this is V sub x. Again, these arrows are called vectors. Well, we kind of know what that is. It's 8.25. And you see, that's not really going to change because we have constant velocity in the x direction. Now, what's going on then in the y direction? Well, there's no up and down velocity at the beginning. So we can say the initial velocity in the y direction, VIY, the initial velocity is 0. But that velocity grows over time, right? Why is that velocity growing over time? Well, we have the influence of gravity. But gravity, again, just acts downward on an object. So this VIY grows over time. It takes time really for gravity to act, right? It acts and causes that velocity to start slow and grow, right? Now, the physics student moves the trash can, but the physics student moves the trash can in a horizontal motion, right? That horizontal motion then, or that distance horizontally, left or right then, where that trash can has to be put is really a delta x idea, right? That delta x idea, when we talk about projectiles or ballistics, that's called the range of the projectile. That's a horizontal idea, right? So what else do we really have here? It says the dorm is 25 meters high. Well, that represents this displacement or distance here, right? So that would be a delta y idea, 25 meters. Okay? That's a delta y idea. That's how far the ball will be traveling downward to the ground. So we want to know, where should the trash can be placed? Okay, so where should the trash can be placed? That's a delta X idea. That's a question mark we have. Also, we need to get the time of flight, so we want to figure out how long the notebook's in the air. Now, with some sports, they'll call this the hang time. Like if you're punting the football, that's the hang time that the ball's in the air. And we like to get the velocity vector. We'd like to get the speed of the object at impact. All right, so we've got really three things we want to get here. How far forward will the notebook travel? How long will it be in the air? And how fast will that notebook hit the ground? That's called the impact velocity. All right, so let me kind of show you how to work this problem. All right, and again, you're going to say, wow, it looks pretty complicated. Well, projectiles are pretty complicated. You know, we've got to use all the equations that we've studied so far, right? So, we know then horizontally that the object's moving at constant velocity. So that'd be x sub f equals to x sub I plus vt. And this v would be v sub x. Well, if we put the x on the other side, this x sub I on the other side, we get xf minus xi equals vxt. But this xf minus xi is a delta x, right? That's what we want to find. That's the range. That's going to equal to vt, or v sub xt. Well, v sub x was given to you, 8.25. This time then represents the hang time. How long is the projectile or notebook in the air? We're not sure what that is just yet. So the problem is we've got these two unknowns, and we can't really figure out what that delta x yet until we get this time of flight. So what we're going to have to do then is to go to another equation. Now, we said then that vertically, the vertical equation represents free fall. So let's put down our how far equation. We said vertically then, how far, delta y, is VIY t plus 1/2 AT squared. Right? That would be how far the notebook or the ball travels vertically. Well, we know this VIY, we know that the object has no initial velocity in the y direction. So this term goes away. And we know then that this represents that the notebook falls 25 meters. So we're going to call this then negative 25. And that's going to equal then to 1/2 negative 9.8 times t squared. Do you notice then that we can solve that for t? All right, do you understand? We can get the time, and that's going to be the time of flight, or the hang time. So in your calculator, you can say, okay, negative 25 times 2 divided by negative 9.8, that's 5.1, but we have to take a square root of that, right? So I'm going to take it to the half power, and I get about 2.26. So this time is 2.26 seconds. So that means the notebook is staying in the air for 2. Now we can put that time in here to figure out then where should we put the trash can horizontally. So let's take this then times 8.25. We get about 18.6 or 18.63. All right, that would be then in meters. So that's telling us that's telling us where the trash can should be placed, how far forward that object goes. All right, in this case it's a notebook. Now, so we've got then the range, we've got the time of flight. Now it's asking us for the velocity vector. So this represents the impact speed. Now with projectiles, impact speed's pretty important. And it's really a combination of two speeds, right? We know that the object is traveling horizontally, but it's also got vertical velocity, right? Well, to get then that vertical velocity, we need to use the how fast equation. So VFY equals VIY plus AT. All right, that's the how fast equation. Notice we're using like all of our equations here, right? Well, we know vertically it's not moving initially. We know then this A represents negative 9.8, and this T represents then, we'd like to get the velocity right at the end of its trajectory. So that T represents 2.26. So we're going to take then 9.8 times 2.26. We get 22.15. Now, we know that's negative, but my arrow is showing downward. Remember that the negative sign really just means direction. So what we can do then is we can really say, okay, that's just really 22.15. So we have a vector 8.25 and 22.15. But we've got to really add these up, right? Because the speed of the object is a combination of those two velocities. But remember, we just can't add up vectors unless they're collinear. These vectors are not collinear, they're perpendicular. So we've got one velocity vector downward, we've got one then horizontal. This is 8.25 and this is 22.15. Remember how we deal with this? This is why we study vectors before we get here. So we make kind of a box and we make then that triangle. You see we have a right triangle there. There's your theta right there. Okay? So what we really want, and I'm kind of running out of room here, but what we really want, let me maybe just put it down here. We've got a triangle that really looks like this, right? Our two legs of our triangle, 8.25 and 22.15. Do you remember how to deal with this? Well, we want to get the hypotenuse. That would be the impact speed. Well, we've got to use Pythagorean theorem, right? So we've got to square this, we've got to square that, and then we've got to take the square, or add them up and take the square root. So on your calculator, I'm going to take, 8.25 squared plus 22.15 squared. Oh, I don't think my calculator like that. Let me try to do that again. 8.25 squared. Okay, I get a number for that. Then I want to add 22.15 squared. Okay, then I want to take a square root. So I'm going to take my answer and take it to the half power. I get around 23.6. Yeah, 23.6, and that's kind of what my answer is here. So do you really understand then? That represents the overall speed of the object. It combines the horizontal and vertical speeds. Now, the important thing too also is to get a theta, right? An angle. Well, that angle then represents a tangent, right? We did this with the projectile unit. So opposite over adjacent. 22.16, 8.25. Now, notice that this is really a fourth quadrant angle, right? So we could say then second tangent 22.16 divided by 8.25. I get an angle of about 69.6, okay, or 69.5. That's kind of what I have down for my answer, depending on how you round it. Well, you can't really report it. You can't really say 69.6 or 69.5, okay, because that'd be a first quadrant idea. But it's pretty easy. All we have to do then is put a negative sign, right? And that's telling you you're going clockwise around your circle then. That's a fourth quadrant idea. So the velocity vector then represents 23.6. That's how fast the notebook is falling right before impact. And it's falling at an angle of negative 69.5. All right? Now, that's just one problem, but it really, I mean, it's a complicated problem because it has everything in it, but that's the analysis of a type 1 parabola, okay? It's a complete analysis. We can get how far it goes, we can get velocities, speeds, etc., how much time was in the air. Now let's look at maybe doing another one, all right? Now, the other one, this other problem's very similar, but again, sometimes they ask you to find different things. This is an example from baseball. It says the distance from a pitcher to home plate is around 18.39 meters. Now, that's an important idea, right? What would that be? Well, we're saying then that the distance from the pitcher's mound to the catcher's 18.39. Well, that represents a horizontal displacement, right? So we're going to call this delta x. Does that make sense? This would be the range or the delta x of the ball. If the ball drops 0.8 meters vertically on the way to the catcher. So what we're saying is we get this trajectory and the ball drops then 0.8 meters. That's going to represent then, that's really negative, that's going to represent then the change of displacement vertically for the ball. So if the ball drops that far, how fast was the ball pitched? So do you see we really want to get Vx here? Because the ball's traveling in a type 1, a type 1 projectile. All right? Well, again, we're going to really use the same equations we used up here. We said really... Hey, my video camera had a little hiccup there, so I'm back though. So we want to get the speed of the ball. That's a Vx idea, because in type 1 trajectories, the ball, in this case the baseball, only has that type of velocity in the x direction, right? So that's a horizontal idea, so we need the x or the horizontal equation. We said then that horizontally the ball's traveling at constant velocity. So there's our constant velocity equation. Or we can write delta x equals vxt. Now, we know what that delta x is here, right? That's the distance from the pitcher to the catcher. That's going to be 18.39 equals then vxt. We don't know the Vx, that's what we're trying to find, right? But we don't know time. That's the same idea as in the previous problem, the time of flight, right? Or the hang time. We want to know then how long the ball is in the air, or how long will the ball take to get from here to here. Well, we were able to get the time of flight using the how far equation. Well, let's look at that idea again. We said that the delta y is VIYT plus 1/2 AT squared. Delta y is VIYT plus 1/2 AT squared. Well, this term goes away. Why? Well, initially the ball has no vertical velocity. So the delta y would be then the vertical displacement the ball drops. That's given to you. That would be equal to 1/2 a. Well, a is negative 9.8 t squared. Again, we can easily solve that for t. Okay, so what we have then is negative 0.8 times 2 divided by 9.8. Again, that's going to be negative. The two negative signs cancel out. Okay, then we want to take a square root. So we get a time of flight then, or that the baseball's in the air about 0.404 seconds. Right? Let me get that up so you can see. The time of flight is 0.404. So that's going to go here, right? So now we can solve for v sub x, right? We can take 18.39 divided by 0.404. 18.39 divided by 0.404. Oops. 0.404. And that's going to give us a speed of about 45.5 meters per second. Now, in baseball, we typically measure speeds in terms of miles per hour for a pitcher, right? Well, that 45.5 is pretty similar, or using conversions, it's about 102 miles per hour, all right? That'd be pretty good for Major League, wouldn't it? All right. Hey, this is kind of the way we do type 1 projectiles, all right? Now, they look complicated. Well, they are kind of complicated, okay? We're going to do some more practice, though, because you definitely need more practice, don't you? Hey, talk to you later, kids. Bye.